Now we have laid the ground for base 10 system. We can also start to add and subtract and multiply and divide efficiently. Of course, if you have small numbers, for example 2 plus 3, we don't use an algorithm, we just remember that this is equal to 5. Or if you have 23 plus 45, it's easy to see that we have 2 tens and 4 tens, then we have 6 tens, 3 single ones and 5 single ones, we have 8. But if you have larger numbers, we need to use algorithms to be efficient. So in different countries and different culture, and also inside different countries, they use different algorithms. But most of them used worldwide are quite similar. It's only superficial differences, with some notable exceptions, but it's basically the same idea. So it's using the base 10 system. So let's start look at the addition. So how can we use algorithms to calculate in addition? So these are those standard algorithms. So let's take an example of 154 plus 368. So how can we do this efficiently? In the addition algorithm, standard algorithm, we put them under each other. And this symbolizes that we put piles of the same type under each other. So here in this column we have singles. You can think of single balls. We have 4 single balls and 8 single balls. And here we have these 10 piles we have seen before. So these represent, each number here represents one of these piles. So we have 5 10 piles and 6 10 piles. And here, now we can't write everyone, but here we have these huge piles of 100. So these are huge piles of 100 here. So we have 1 of those and 3 of those. So we put piles of the same type in under each other vertically. So then we can be efficient when we start adding. So then we only need to worry about adding single digits. Of course, we're adding single digits here now, and implicitly we're adding piles of the same type. So if you have 4 singles and 8 singles, then we have 12 singles. But instead of writing 12, we only keep the single ones here. We have 12, we have one pile of 10, and that pile belongs in this column. So that we move up here and place in this one when we add here. So we mark here that we got one 10 pile from the single ones. And now we can add the 10 ones. So we have 6, 12. Again, 12 of these 10 piles. Okay, so we write 2, meaning we have 2 10 piles. But since 12 here now means we have 100 pile and 2 10 piles. This 100 pile we move up here. So we've gotten 12 here, and the 1 here means we have 100 piles. So it belongs in this column. So now we have 500 piles. So this is of course how we add with the addition algorithm. We add up piles of the same type. And we do it from right to left, because that's the most efficient way of doing it. We could of course go in this direction also, but then sometimes we have to go we have to go back. So it's possible but less efficient to do it from left to right. Okay, so that's the addition algorithm. And then we can do similarly for subtraction. So let's take another example for subtraction. So let's say that we want to subtract 325 and 147. So again we put them under each other, so we have the corresponding piles under each other vertically. So this means now we have 5 single ones and want to remove 7. So if you start removing the single ones. But of course you can't remove 7 from 5. So we have to exchange one of the 10 piles. So if we take one of the 10 piles we have here and exchange it to single ones, and we mark this by putting a line over it means that we have taken one of these 10 piles and then we use it here. So one 10 pile gives us 10 single ones. So then we have 15 single ones minus 7 single ones, and it gives us 8 single ones. So now it wasn't possible to do this step because we borrowed, you could say, or exchange, maybe a better word. Now we do this 10 piles. Now we have 1 here, not 2, but 1 10 pile, and want to remove 4, and that's neither possible. So we borrow from the 100 piles, or exchange from the 100 piles. So we exchange one of the 100 piles here, then we get 10 piles. So 10 piles and 1 10 piles. We have 11 10 piles minus 4 10 piles. And then we have 7 tenths. And then finally we do the hundreds. Here we have 2 minus 1, that's 1. So we end up with 178. So also here we work from right to left. Not because it's necessary, but for efficiency reasons. We could do this also, but it's not as efficient. Okay, so that's how the addition and subtraction algorithm works. We exchange whenever we got more than 9 of something. Or here we exchange from larger one when we need something to subtract. For multiplication, there are many different variations used worldwide, but most of them only superficially different. So we will just use one of them here. If you understand this, you will understand most of the others because it's only superficially different. So let's take 123 times 789. Okay, so how will we do that using the multiplication algorithm? In this case, we can of course write it in vertically also. So let's do that. And now we don't have plus here, but multiplication. So we start here with multiplying the single ones. So this is the method to doing this algorithm. You start with a single one of this. So you multiply with a single one of that. So 9 times 3 is 27. You only keep the 7 here, the single one. And 2 we keep in memory, because this 2 now represents tenths. So this is 2 tenths. And now we multiply 9 and 2. So now we will first see how it works, and then we'll explain why it works the way it does. So now we want to multiply 9 and 2, and that's 18. But adding also those we had here, 18 plus 2, so 20. So we have 0 and 2 in memory. Then we multiply 9 and 1 plus these 2, that's 11. And now we can write 11 since we don't have any more multiplication with this 9 here. Then we start with the next digit. We want to go through all the digits here of one of the numbers. So we take 8 times 3, that's 24. And now we write the 4 here, but not here, but one step to the left. That's the method of the algorithm. So 8 times 3 is 24. So we put the 4 here and 2 in memory. 8 times 2, that's the next step, 16, 18. So we put 8 here and 1 in memory. And 8 times 1 plus 1, that's 9. Then on the final step we do this 7 multiplier. 7 times 3, 21. And again we move one step to the left, so we put the 1 here. And 7 times 2 is 14, plus 2 is 16. And 7 times 1 plus 1, 8. Now we have done all the combinations. We have done 9 multiplications in total. And now we need to add up all these. If you like, you could think, or we could put zeros here. It's not necessary, but that's what it really means. This number is actually that. So now we want to add them up just using the normal addition algorithm. So 7, adding nothing. 0 plus 4. And this is 10. So we put exchange 1 to the thousandths. So this is 10, 11, 17, and 9. So here we have the answer. And then we want to explain, now we have explained the method, but now we want to explain why it works the way it does. So let's explain this in this way. Now we will use the rules we have gathered from previous lectures and the base 10 system, positional system. So 123 we can write as 1 times 10 to the power 2 plus 2 10 to the power 1, or you can skip the 1 there, and 3, and multiply that by 7 times 10 to the power 2, 8 times 10 plus 9. So this is using the positional system base 10. And now we can use the rule of multiplication of sums that we have seen previously a rule for. You need to multiply all combinations here. So that times that times that. So we get 9 multiplications in total, since it's 3 times 3. So we start with this one. So it's 1 times 7. And then 10 to the power 2, 10 to the power of 4. 10 to the power of 2, but it becomes 10 to the power of 4. So multiplying these two, we get 1 times 7, and then 10 to the power of 4. Then continue in this fashion. 1 times 8, and then that becomes 10 to the power of 3. And then we get 1 times 9, 10 to the power of 2. Okay, so we just continue in this fashion. So I will just write down the answer here now. So now we see I have done all the combinations. For example, the next one was here, this here times this one. So 2 times 7, and then 10 to the power of 3. So we get this long answer with 9 addition, we add 9 numbers. And then in the next step now, I want to rearrange them a little bit. So I put some of them vertically under each other. But it's same calculation, but only superficially putting them different on the paper here. So now I will do that. So now I have written the same expression as here, but I put them a little bit differently placed on the paper. So you see this one here now. What is this one? This is just this one here. So that's the same as that one. So in that way, I just take them and put them differently. So this one is that. So this one, 9 times 2 is this one. 9 times 3, this. 8 times 1, there. 8 times 2 is this one. And 8 times 3, this. And 7 times 1, 7 times 2, and 7 times 3. So you see now we have taken all of them, we also put them differently. And the point here was to put all of them with the same base 10 power under each other. So here I have all the tens, here are all the singles, here are all the hundreds, all the thousands, and all the 10,000s. So now I see that I can add, if I add them up now, like this. So you can add them up vertically. It doesn't matter in which order I add them up. So what's the point of that? The point of that is now we can see that, for example, this one and this one, all of these now are all the multiplications, single digit multiplication that we did in the multiplication algorithm. So if we remember now, we had the algorithm. We put 1, 2, 3, 7, 8, 9. When we started, we did 9 times 3, and that's that one. Therefore, it belongs in this group. So we put the answer here. Then we took 9 times 2, that's this one. Then we took 9 times 1 is this one. And we see we put them in this order because now they're raising a power of 10. So we put them in correct order. And then we jump to 8 times 3. And that's answered here. And the reason we put that one step to the left, we see here because now it has a 10 belonging to it. So it belongs here. And then 8 times 2 is this one. 8 times 1 is this one. And the final step, we multiply 7 and 3. And also move that one to the left because there it belongs with 100 after it. So we see that we get all this single multiplication. That's the reason for the structure we do here in the multiplication algorithm. So we see this is just using base 10 position system and the multiplication of sums rule that gives us this, and just placing them a little bit smart in columns under each other with the same base 10 powers under each other. Then we get just the normal structure of the multiplication algorithm. Then we finally come to division, the division algorithm. So let's see first how it works, and then we'll explain why it works. So let's take an example here. And then again, there are different variants of this division algorithm, but most of them work in the same way, so it's only superficially different. So let us now start with seeing here, if we now want to find out how many times does 12 go in the first digit. So now we start from the left here. How many times can you multiply 12 to get 1? Yeah, you can... or how many times can you divide 1 into 12? Yeah, 0 times. So if you take now 0 times 12, what's that? That's 0. Then we put 0 here. So again, I remember that this is just to explain the method. And then we've got a 0 here, but then we take away 1 minus 0, that's 1. Okay, this first step was a little bit unnecessary perhaps, but we want to keep it like an algorithm, doing the same step all over and over again. So we got the 1. The next thing we do is we take down the next digits. So because we could have started with 17. Then the next step we see here, how many times does 12 go in 17? So if we divide 17 and 12, we can take 12 one time. And 1 times 12, how much do we get left then? So we multiply 1 times 12 is 12, then we remove, then we get 5 left to divide up. And then again we take it down, the next digit. Now we want to see how many times does 12 go in 55. Yeah, it's 4 times. So 4 times 12 is 48. And subtracting that, see how much we have left. And now we need to do the subtraction algorithm, but it's an easy subtraction, so we can just write 7 directly. Then we take down the last digit. How many times does 12 go in 72? Yeah, 6 times. And 6 times 12 is exactly 72. And now we don't have any more digits to take down. And also we have gotten a 0 here. That means that we have come to the end of the algorithm. So the answer is 146. So 1752 divided by 12 is 146. So that was the method. Now we want to explain why it works the way it does. So if we could of course think of money. It's easy to think of money. So let's say we have 12 persons. 12 persons want to divide up equally this amount of money. So they get the same amount. And then we could start with dividing up the thousands. If you have $1,000 bill and the currency and 12 persons, it's not enough. If you have 1/12, we can't divide it up. So they will get 0. Each person will get 0 of these $1,000 bills. Okay, so we divide up that's nothing. So how much do we get left? what we want to see now is that after you have divided them up, but we haven't divided anything up, so you have removed nothing. So this is how much we have divided up so far, but we haven't divided up anything. So in the next step, we see that now we will exchange this to hundreds. Instead of having $1,000 bills, we exchange these thousands to 10 hundreds, and we add those we had before hundreds. So now we have $1,700 bills. And 12 persons dividing up $1,700 bills, then we get $100 bill each. Okay, and if we divide up these 12 $100 bills, how much do we have left after dividing up equally? Yeah, each one you will get 1. So we have divided up 12 of them. That means we have 5 left. So we have 5 $100 bills left. Okay, how do we divide up that? Yeah, we exchange those to $10 bills. And 5 $100 bills is 50 $10 bills. But adding those we already had 5. So now we have 55 $10 bills. Okay, so how much of these 55 $10 bills will each person get? Yeah, we see that they can get 4 each, because 4 times 12 is 48. We can't take 5, because 5 times 12 is 60, and we don't have that many. So they get 4 each. That means we have 7 left. 7 $10 bills left to divide up. And they have gotten 4 each. And then we exchange these 7 $10 bills to $71. But we already had 2. So now we have $72 left in single coins to divide up. So how much do each person get then? Yeah, 6. Because 6 times 12 is exactly 72. And after that we have nothing left. And we have no digits left. That means we have no money left. That means we have divided up everything. And after you divide up everything, each person has gotten $146. So that's the method of thinking. And of course, instead of dollars, we could think of these piles we had before: 1,000 pile and 700 piles and so on, dividing up the piles evenly. So we just divide up each type of pile evenly as much as possible, and that's what is remaining we exchange to a lower value pile, and we continue in that fashion until we have nothing left. If we, for example, instead would want to divide up this, then in the final step we would have ended up with 1, not 0. So after having done all these steps, we would have ended up with 0, 1, 4, 6. But we would end up with a 1, and we have no more digits left to work with. And that signifies when you are finished with all the digits in the algorithm, but you still don't have 0 here, that means that the division didn't go up. So it means that you are left with a remainder. So that's a remainder. So that means that this is equal to 146 with the remainder of 1. So each person will get $146, but then we are left with $1. Then we could, of course, continue to divide up this into cents and so on. But for the moment, we will stop here and we come back to that when we talk about decimal numbers. So in this case, we just keep the remainder. No one gets this, it's just left outside the division.